In this final part of the lecture, we are going to look at a few examples of proofs that illustrate the use of our quantifier rules. Here's the first example. We want to prove the conclusion BD from two premises. The first premise is that there is an x such that kx, and for all y, if y is k, then x is identical to y, and bx. So what we are saying here essentially is that there's exactly one k, and that k is a b. And then our second premise is kd, meaning that object D has property k. And from these two premises, we want to prove that object D also has property b. Now, how can we do that? Let's reflect on our strategies. Now, backward planning suggests look at your conclusion, identify the main connective, and use the corresponding introduction rule. Now, that doesn't work in this case simply because our conclusion here doesn't have any connectives. It's an atomic sentence. So let's move on to forward planning. Forward planning suggests look at your premises and use the corresponding elimination rule. And that's what I'm going to do here. So our first premise is an existentially quantified sentence, and I'm going to try to prove my conclusion here using existential elimination. Now, how does that work? I set up a subproof. I start my subproof with the assumption that Ka and for all y, if ky, then a equals y and ba. So here I've simply taken the sentence from the first line and deleted the existential quantifier and then replaced the variable x by the name a. And from this assumption, I now want to prove BD, since if I'm able to prove this, then I'm licensed to infer BD down here using existential elimination, citing line 1 and the subproof from line 3 to somewhere else. Okay, so this is my basic proof setup, and my basic proof strategy is suggested by forward planning. Now in the next step, I'm going to observe that here we have a long conjunction with 3 conjuncts. So I'll just make my life easier and simply separate these 3 conjuncts. So each of these steps is justified by conjunction elimination applied to line 3. So what do we have in our proof now? We know that object A is k, and we know that for all y, if y is k, then A is identical to y, and we know that BA. And we want to prove that BD. Okay, so we also have a little further up in our proof the premise that KD. So I am going to use universal elimination to infer that if KD, then A is identical to D. So this step is justified by universal elimination applied to line 5. So here I've simply taken my universally quantified sentence, deleted the universal quantifier, and substituted the name D for the variable y. And this gives me a conditional here. If KD, then A is identical to D. Now I also see that I have the antecedent of this conditional in line 2. And that means that I can infer A equals D, the consequent of my conditional, using conditional elimination applied to lines 1 and 7. And now I can infer BD using identity elimination and lines 6 and 8. So if A has property B and A is identical to D, then D must have property D as well. Then D must have property B as well. And that completes my proof. Now I only need to fill in the final gap, so we can conclude that BD, using existential elimination, apply to lines 1 and the subproof from 3 to 9. And that's it. So in this proof, we want to prove a universally quantified sentence. Namely, we want to prove that for all x, either px or x is not identical to A. And we have one premise to work with, and that premise is that A is P. Now, how can we prove that? I'll start by applying backward planning. Backward planning suggests to use universal introduction. And that requires us to first prove a sentence of the form PC or not C equals A. Since if I'm able to prove that, then I can infer my universally quantified sentence using universal introduction. Now my goal has shifted. I now want to prove this disjunction. From experience, I know that it's usually hard to prove a disjunction using backward planning. And forward planning doesn't work in this case, since our one premise in this proof does not have any connectives. So that leaves me with my third proof strategy, which is indirect proof. So I'm going to prove this disjunction using IP. IP requires me to set up a subproof that starts with the negation of what I want to prove. So I start out by negating this disjunction here. And I want to derive a contradiction from this assumption. Now, how can we do that? Well, here I see that I have a negated disjunction, and that reminds me of De Morgan's law. So I can infer a conjunction where both of these disjuncts are negated. Not PC and not C equals A. I make my life easier and apply conjunction elimination to these two, to this conjunction here. So that gives me not PC in line 4, and it gives me not C equals A in line 5. So line 3 is justified by De Morgan's law applied to line 2. Line 4 is justified by conjunction elimination applied to line 3. And line 5 is also justified by conjunction elimination applied to line 3. And now I see a double negation here, so I'll just go ahead and eliminate this double negation, which gives me C equals A, justified by double negation elimination applied to line 5. Okay, and now I see that C equals A, and I also see that A is P. So that allows me to infer that C is P using identity elimination applied to line 1 and line 6. But now I see that I have the sentence PC in line 7, and I have the sentence not PC in line 4. So these two lines contradict each other, which allows me to infer bottom using bottom introduction applied to lines 4 and 7. And now I can infer PC or not C equals A using indirect proof and citing the subproof from 2 to 8. And I can infer my final conclusion using universal introduction applied to line 9. So that's our final proof. Okay, let's look at a third example of an FOL proof involving quantifiers. I want to discuss two proof strategies. We are first going to look at a proof strategy that does not work, and then we are going to look at a proof strategy that does work. So the proof strategy that does not work in this case is backward planning. Let's see why. So I do want to prove an existentially quantified sentence of the form there is an x and there is a y such that x is not identical to y. And I have two premises to work with. There's an x such that jx, and there's an x such that not jx. Now, backward planning suggests that I should infer this conclusion using existential introduction, meaning that I would need to prove a sentence of the form there is a y such that not a equals y. And applying backward planning once again suggests that I then should prove this sentence using existential introduction, which would require me to prove a sentence of the form it's not the case that a equals b. So this is the proof setup suggested by backward planning. But now the issue is that I am not going to be able to prove that a is not identical to b from my two premises. And why is that? Well, the first premise just tells us that some x is j, and the second premise tells us that some x is not j. So these two premises don't give us any information about the two objects a and b. They just give us general information about two objects of some kind. So I will not be able to infer a claim about the specific objects a and b from the two existentially quantified sentences that I have as my premises here. And that's why backward planning does not work in this case. Okay, let's look at a proof strategy that does work. So we can prove this conclusion using forward planning. Forward planning suggests to look at our premises, in this case two existentially quantified sentences, and to use the corresponding elimination rule. And that's what I'm going to do here. So I will start out by setting up a subproof that starts with the assumption that JA and ends with the conclusion that there is an x and there is a y such that not x equals y. Since if I'm able to do this, then I can infer my overall conclusion using existential elimination applied to line 1 and the subproof from line 3 to somewhere else. Okay, so that's my new proof setup. To make progress in this proof, I will apply forward planning once again. So I will set up a second subproof that starts with the assumption that not JB and ends with the conclusion that there is an x and there is a y such that not x equals y. Since if I'm able to do this, then I can infer my conclusion here using existential elimination applied to the existentially quantified sentence in line 2 and the subproof from line 4 to somewhere. Okay, so that's the state of the game now. We want to prove that there's an x and there's a y such that not x equals y, and we have 4 premises to work with. And I'm here going to focus on the two premises JA and not JB. These two premises should allow me to prove that A is not identical to B. And that's then going to help me to prove my doubly quantified sentence down here. So I will try to prove that there is a y such that not A equals y. And I am going to try to prove that it's not the case that A equals B. So if I can prove that it's not the case that A equals B, then I can infer this sentence here using existential introduction. And I can also infer the subsequent sentence using existential introduction. Now, we want to prove that it's not the case that A equals B, the main connective here is the negation sign. So backward planning suggests that I should prove this using negation introduction. So I'd set up a subproof that starts with the assumption that A equals B and ends in a contradiction, since then I can infer that it's not the case that A equals B using negation introduction applied to the subproof from line 5 to somewhere. Okay, so from the premise that JA and A equals B, I can infer that JB using identity elimination applied to lines 3 and 5. And then I can infer bottom using bottom introduction applied to lines 4 and 6. And now I can infer that it's not the case that A equals B using negation introduction applied to the subproof from 5 to 7. And then I can infer that there is a Y such that A is not identical to Y using existential introduction applied to line 8. And I can infer that there is an X and there is a Y such that X is not identical to Y using existential introduction applied to line 9. And now I can infer the same sentence once again using existential elimination applied to line 2 and the subproof from line 4 to line 10. And I can infer my overall conclusion, again using existential elimination applied to line 1 and the subproof from line 3 to line 11. So that completes our proof, which we were able to successfully complete using 2 applications of forward planning.